Hi guys, this video is about kind of scattering in one dimension and the calculation of what are called transmission and reflection coefficients. Now I'm going to deal with one dimension in this video, but when we get to scattering in three dimensions, some of the ideas are quite similar, so it's good to start here. But let me show, again, most of this video will be on my notepad. So we will start going through the math here. So what we want to describe is a beam of particles, right? Well, I should say electrons or other quantum particles. And to do this, we can do this in three dimensions pretty easily. We realize that the wave function going in the y and the z directions, right, in the plane perpendicular to the speed of the particles, is pretty much constant over this square or rectangle and zero everywhere outside. So again, what we have is basically a wave function that's only going to depend on x and be constant in the y and the z directions here. And we recall that the probability of finding the particle somewhere in this volume is the integral over the volume of psi square psi, or the absolute square of the wave function. So one thing that happens is that it turns out the probability can be treated like kind of like a fluid, and it kind of can flow out of the volume or into the volume. In our case, we should happen, there should be a flow of probability to the right along the x-axis, showing that that's the way the particles are moving. Any fluid or other quantity like heat that has to be conserved, and we need to conserve probability, we can't just lose probability, obeys what's called a continuity equation. And so the derivative of the probability with respect to time is equal to the change or loss, denoted by the negative sign, of this quantity, where J is sort of a current. It's a heat current or a current of fluid moving out of the volume, right? So we should have a probability current going along the x-axis. And I'm not going to derive the expression for probability current here. It can be done using the Schrodinger equation. Maybe I'll make a video on that later if there's interest, but it can be shown. And again, the upside down triangle sign here, if you haven't seen it, is a gradient. It's just derivatives in the x, y, and z sort of directed along the unit vectors x hat or I hat, j hat, and k hat, right, along those specific directions. But it can be shown that the probability current for quantum physics or quantum particles is given by this expression. And there's a gradient function in here, which we can kind of get rid of, or just if we focus on one dimension, we notice that the current in the y and the z directions should be zero, right? Because we have a beam just going to the x. So there's no current going up or down or in or out of the page here. So in our situation, we should have only derivatives. This gradient becomes just derivatives with respect to x. Now, typically in an experiment, we would create a beam of particles with a constant momentum or speed. And remember, quantum expression for momentum can be written as h bar k, where k is the wave number of the wave related to the wavelength. Velocity is momentum over mass, right, mv over m, or h bar k over m. Now this means that if we have a free electron wave function that can be described by sines and cosines, or this e to the I kx minus omega t function, right? We have a e I to the phi, where I'm just denoting phi as the phase, kx minus omega t. We can easily calculate the current, the probability current. And if we do that, what you get is this. So just plugging in that a e to the minus phi, taking the complex conjugates, right, changing the i's to negative when we do that, we end up with this expression, h bar k over m times a squared. Now recall, again, h bar k over m is really just the velocity. A squared is kind of the square of the wave function, the magnitude of the wave function. So this is kind of like a velocity times a density, a probability density. And it makes total sense in that way that this is a probability current. It's kind of the probability multiplied by the velocity in the x direction. Now, one thing I should say about this type of wave function, it cannot be normalized. I mean, it is pretty much the same everywhere throughout space. So if you tried to integrate all the way from x equals negative infinity to infinity, well, you get infinity. You can't normalize the wave function. So usually what we deal with in this case are relative probabilities. We set up an incident beam, and when it hits something, it turns into a reflected and a transmitted beam of particles. And so we take the probability of it being reflected or transmitted relative to the incident wave probability. So we'll see how that works here in a minute. But the problem that I'm going to do here today in this video is the potential step. What I mean by that is that you imagine the beam coming in from x equals negative infinity, and then at x equals 0, it hits a potential change, right? The potential change is from 0 to some value, we'll call it V0, right? So I'm drawing it here. So up until you get to x equals 0, the potential is 0. There's no potential, it's just a totally free particle. And then the potential changes to a constant V equals V0 value. And again, I'm saying the electron beam is coming in from the left, negative x to positive x. Now the kinetic energy that the beam comes in with, K or E as I call it, that's the kinetic energy of the particles, right, when they're far away coming in from the left. And I could write my wave number, K, in that region as 2mk over h bar squared square root, or square root of 2me over h bar squared, right? This comes from the Schrodinger equation. And similar to what we had for the infinite square well, but now we've got a different potential energy function here. Again, it's kind of artificial in a way, but it does denote very common thing that happens. So we've got our incident wave number, or our incident momentum sort of vector. When it gets to the region 2, now the potential is higher and there is less kinetic energy, right? So I should say that the kinetic energy really is E minus V0. So let me scratch that out. Kinetic energy is equal to the initial kinetic energy minus V0, and I really should write this as E. So what I end up with is a wave vector in this second region, K2 equal to the square root of 2m E minus V0 over h bar squared. So the total energy remains the same. It's still kinetic plus potential. But what's happened is the kinetic energy has dropped in this second region because now there's some potential energy there. So we've got two different wave vectors. And then we go to the Schrodinger equation. And you might remember a little bit, we can write, maybe we could talk more about the Schrodinger equation again later, but maybe you can show that solutions to the left of the barrier for x equals 0 are like this. And I've not written the omega t part, the time-dependent part. And the reason is because that can sort of be factored out. We'll do this more formally later, but this is kind of a time-dependent thing. We're assuming kind of the beam is just continuously coming in. Particles are hitting the barrier. Some are being reflected. Some are being transmitted. And what I've got to the left of the barrier is an incident wave, denoted by e to the I k1x, right? So this one's sort of going this way, plus b e to the minus I k1x. So this is the reflected wave. And again, this comes because of the current. If I calculate the current for this type of wave with a minus, I would get minus v times b squared, or minus h bar k over m times b squared. Now to the right of the barrier in region 2 here, I've got another wave, but it's wave number has changed to K2. So now it's CE to the I K2 times X. All right, so those are the solutions to my Schrodinger equation in those two regions. And a common thing that happens is the Schrodinger equation is a differential equation. So we have undetermined constants. And these constants are determined by boundary conditions or matching conditions. In this particular problem, we are going to match these solutions and their first derivatives at x equals 0, where the potential changes. Since it's a second order differential equation, the Schrodinger equation has to have solutions that are continuous, right? So they are the same. They don't change suddenly when you jump here. If it's a real physical thing, there can be cases where that's not the case. But generally, well, actually, I guess it's always true. The wave function should be continuous everywhere in all the ranges of the full range of x. Not only that, but the first derivative should be continuous. Otherwise, we couldn't take a continuous second derivative, right? It would be different in one place than another. So these are going to be our matching conditions at x equals 0. When we do scattering in 3 dimensions, we end up with a very similar thing. We always have to match the wave functions. Now, when we match, we first of all match the solution in region 1 to the solution in region 2, setting x equal to 0. All the e to the I kx's go to 1, and I get a plus b equals c. Taking the derivative, we'll pull out I k's in front of the functions, and setting x equal to 0 again. What I end up getting by matching derivatives in region 1 to derivative in region 2 is ik1a minus ik1b equals ik2c. And now I can solve for the relative probability amplitudes. I can solve for the relative probability amplitude of being reflected to the incident probability amplitude, b over a. I can let you work through the algebra if you'd like, but this is the result you get, k1 minus k2 over k1 plus k2. And I could also do the same thing for the transmitted probability amplitude, c over a. And I end up getting 2k1 over k1 plus k2. Okay, now, once we have those relative probability amplitudes, we want to get the relative probability for reflection and transmission. So we'll look at the reflection coefficient. This is the probability that the beam or the particles are reflected. Right? And so what I need to do is I take my reflected density, or sorry, current, over my incident current. Now my reflected current is, again, right, going back to this definition. I'm going to show it here real quick. It's h bar k over m times the amplitude squared of the wave. So for the reflected wave, it's b squared times h bar k1 over m. Incident wave, a squared times h bar k1 over m, and I divide to just get b squared over a squared. So basically, I'm going to just square this. And so my probability of reflection is k1 minus k2 over k1 plus k2 squared. Now, one thing you can show, and maybe I won't show it here, is that this should go to 0 when your kinetic energy is equal to V0, right? Basically, your K2 goes to, or sorry, it should go to 1. If you get below the barrier, your kinetic energy is below the barrier, there's no way to get through. There's not enough kinetic energy to go over the barrier. So this reflected coefficient should go to 1. And you should see that K2 goes to 0. And so you get K1 over K1 squared, which is 1. So again, just to emphasize what these probabilities mean, what this reflection coefficient means is that it's the probability of being reflected. So a way to interpret it is, let's say you have 1,000 particles coming in. If your R is 0.25, you should get 250 reflected and 750 going through transmitted. You could also think of it as the probability for one particle. It would have a 25% chance of being reflected or a 75% chance of being transmitted and just continuing on over the barrier. Now, what about the transmission coefficient? It's a little bit different because my density or my probability current changes. My transmitted current is c squared times h bar k2 over m, right? Because my wave number has changed when I go into that second region. Divide that by the incident probability current, ji, I get c squared over a squared times k2 over k1. So if I square, and I take this, right, I use my c over a from up here, square that, multiply by k2 over k1, I get my transmission probability of 4k1 k2 over k1 plus k2 squared. And you should also be able to show that r plus t equals 1, which just denotes this kind of law of conservation of probability. I can't lose probability. It's always got to add up to 100% or 1, right? It's either reflected or transmitted. It couldn't just disappear. So I will stop there. Hopefully that makes some sense, and maybe I will give you some problems related to this. But this does show kind of a very basic example of the way we do scattering in quantum mechanics, at least in one dimension.